Hello, my name is Evgenii Neverov, and today I would like to present a paper development of the detecting system of the landmark text to increase the navigation accuracy of an unmanned vehicle in a known location. The study purposes landmark detection system for use in unmanned vehicles based on NVIDIA Jetson embedded device. To solve the positioning problem, satellite navigation systems such as GLONASS and GPS are mainly used. The advantage of CNS is sufficient outdoor positioning accuracy and global coverage due to the large number of satellites. The disadvantages of CNS include inability to determine the location in closed spaces, as well as great dependence on weather conditions. Also, the disadvantages include insufficient accuracy in the task of positioning the UAV. These shortcomings can be corrected by using additional methods of UAV navigation, namely the use of computer vision methods. This method serves to support UAV navigation in case of failure of main navigation systems. This paper deals with the use of artificial intelligence tools, namely deep learning and the methods of computer vision for detecting landmarks during the movement of the UAV in harsh climate. The need of additional methods of orientation issued to the problems of the navigation system described earlier. The most commonly used method is localization by means of a GPS module. However, to operate an unmanned vehicle in changing conditions, including premises, imposes restrictions to use global positioning system. The lack of suitable datasets in the task other than urban environment leads to the necessity of developing own simulation, followed by the generation of dataset in conditions close to expected. Based on literature review, the following tasks were concluded. Navigation should be carried out autonomously. The second, due to UV functioning in an outdoor environment, these few features to retrieval radar-based systems are not suitable. The third one, the use of computer vision-based system is possible provided that orienting marks are added to the terrain. Orientation marks must be recognized under different weather conditions, for example, rain and snow. The presence of unique data for research is one of the main parts in computer vision. The data can be used for object detection, segmentation, classification, etc. Despite the fact that there are a large amount of data in public domain, there was a problem with lack of required data since the tech model was developed for detection in winter conditions. To solve this problem, NVIDIA SDK tools were used to generate synthetic dataset. NVIDIA has developed ISAC software for the development of robotic systems and work with artificial intelligence. This technology allows robotic systems to be deployed with subsequent GPU computation, which increases the speed of computing vision models. Detection methods based on convolutional networks require a large number of labeled samples to train parameters, but in general, getting a lot of labeled real data can be tricky. To make up for the lack of training images, NVIDIA proposes a simple method for creating images which is present on the slide. The choice of yellow V4 architecture is based on the fact that yellow V4 indicators are located on the Pareto optimality curve, figure 2. And outperforms the fastest and more accurate detectors in both speed and accuracy, which improves performance in real time. Some YOLO releases, such as Tiny YOLO, allows models to be deployed for embedded devices, and it's possible to involve CUDA cores and significantly speed up the inference of the model, i.e. to increase the frame rate. At this stage of research, testing will take place in Unity 3D using the ISAC Unity 3D allows to use ISAC SDK tools in this simulational environment for robotics. ISAC Sim Unity 3D provides an expandable test environment to evaluate the performance of Isaac navigation stack. It also provides an infinite stream of fully annotated training data for machine learning. Features include simulation of sensors, hardware, and durable-based models, scenario randomization, and scenario management. For the task of detecting objects, such as a measure of average accuracy, is usually used and obtained from two indicators, precision and recall. Precision denotes the percentages of true positive among all results for this class. Mean average precision and also IOU. Intersection of a union is a metric used to assess the accuracy of algorithm that detects objects. The IU value is equal to the quantity of the area of intersections of the predicted framing window and response window from the ground truth area by union of these windows. For example, figure 5. After the process of labeling the data, the stage of training was performed. Training data is presented as the form of ratio of the image with the TXT file on and corresponding label. As mentioned earlier, the transfer learning training the model took place on pre-trained MCE COCO scales, since it contained the basic patterns for the label. The original data was generated synthetically and was close to ideal, which could lead to poor results, and because of that, affine transformations were performed. Initially, the training was organized on 1,563 images with a size of 640 by 4080. And duration of 2000 epochs. However, the output had a low accuracy rate for objects located further than 10 meters. To solve the problem, affine transformations were applied. In turn, affine transformations create new images by changing the color, tilt, reflection, zooming, scaling, and noise the original image. As a result of additional training, changes the data, there was significant increase in accuracy, table 1. The increase of accuracy was due to the fact that initial training was performed of similar equidistant generated data. When testing the detection of landmark objects of the model carried out the remote data, the neural network could not recognize small objects. However, scaling the data improved MAP and IU. In turn, additional training took place over 1,000 epochs. Training datasets and on dataset without affine transformation and dataset with affine transformations is in table 1. The next experiment was aimed at measuring MAP and with and without affine transformations. The measurement performed on the data created in the Unity 3D environment. The data was created in a way to simulate snow conditions. The distance from the camera to the object is comparable to real proportions. As a result, the experiment 100 images were measured at the distance of 10 meters, 20 meters 30 from camera to the object. The result of the experiment are presented in the figure. Results. The real-time landmark detection system model was implemented on the NVIDIA Jetson Xavier. The final mean average precision was resulted in 83.8%. Outlook landmark detection systems using yellow V4 algorithm followed by deployment of NVIDIA Jetson was proposed in the paper. In order to deal with real-world data, yellow V4 neural network was trained using synthetic dataset. Yellow V4 structure was tweaked to create more robust landmark detection functionality. This training method is suitable for creating a model with no or small amount of data. And further step is the development on this three-level system for landmark detection. Thank you for your attention, and bye.